Okay, let's talk about higher order derivatives. These are very important in physics. So the derivative is a function. Many functions are differentiable, meaning we could take the derivative of the derivative. So you get some original function, you take his derivative, you get a new function. You might be able to take the derivative again and get a new function and so forth. We call these higher order derivatives. So the number of little slash marks here is the order of the derivative. This guy here would be the second derivative, the derivative of the derivative. Here we've taken 3 derivatives. After you get past 3, it's too hard. I don't want to put 7 little slash marks and have to count. So after 3, we start using this notation here. This would mean 4th order derivative. You got an original function and you've taken 4 derivatives. We put it in parentheses so that it doesn't look like f to the 4th power. That would be something completely different. These are not exponents. And of course, we could write that in Leibniz notation. So this looks weird. Nothing is squared here. Like if I write this guy here, the second derivative, that would be the second derivative of y with respect to x. And I know that looks like x squared there. I didn't invent this notation. I personally don't like it. I think it's bad notation and it causes confusion. This is not x squared. That's not d squared. This is the way we write. Take 2 derivatives of y and x is your independent variable. It's just a fancy way of writing this. You'll see once you get to calculus 3 why we write it like this. When we have mixed partials and we might have a dx and a dy down here in the bottom. For now, this notation, nothing is squared here. This just means 2 derivatives. And like this guy here would be 4 derivatives. That's not x to the 4th. And keep in mind always that this is not a fraction. This is not d squared y divided by dx squared. It's not what that means. This just means this. So let's do it. Let's calculate this guy's second derivative, and we're going to do it using the definition of the derivative. So his first derivative, I'm going to go through this quickly since we've done a bunch of these. This is the limit as h approaches 0 of f of x plus h minus f of x all over h. So that'd be limit h goes to 0. We got to write that at every step. Twice x plus h squared minus 3x plus h plus 1 minus, and then I subtract the original all over h. So that'll be limit as h approaches 0. Going to expand that binomial there, and you should know by now that's x squared plus 2xh plus h squared. I'm going to do all my distributing here. Don't forget that plus 1 there. And distribute this minus. All over h. Don't forget your over h. Distribute the 2. Don't forget to write limit as h goes to 0 at every step. Pretty soon, we're going to learn all the shortcut rules for taking derivatives, and then we won't have to write all this out anymore. That'll be after test 1. Okay, if you've done this right, everything after that minus should cancel out. 2x squared, negative 2x squared. Minus 3x plus 1 minus 1. Everything, if you have a polynomial, everything after that minus will cancel out. Everything that's left should have an h in it. So I have 4xh plus 2h squared minus 3h. I got that guy, and that guy all left, all over h. And I need to make this a little smaller. And we factor our h out and cancel it. I'm just going to do that in one step here. If you're not sure of it, check this on your own, but I'm going to factor out the h and cancel and get 4x plus 2h minus 3. And I've mentioned a few times, it's perfectly fine if you can do this step in your head to just do it in your head. Now we actually take the limit as h goes to 0 by plugging in h equals 0. I don't write limit anymore because now I've done the limit and I get 4x minus 3. So that's the first derivative. F prime of x was 4x minus 3. Now I got to do the same thing again on this guy and find the second derivative. So I'll do that over here. This one will be quicker. That's, by the way, you should have noticed by now. The derivative slope of tangent lines for a linear function, they all the tangent lines have the same slope. It's just the slope of the line. We're going to get 4 here. F double prime of x is the derivative of this guy, the limit as h approaches 0 of f prime at x plus h minus f prime at x all over h. That's the limit as h approaches 0. So now I'm just replacing the x with x plus h in parentheses. Don't forget that minus 3. Minus the original. Here's f of x plus h, f prime of x plus h. Here's f prime of x all over h. And now we just distribute and clean up. Well, we got 4x plus 4h minus 3 minus 4x plus 3 all over h. Everything after that minus is going to cancel out. See, I almost wrote down that 3. I almost wrote here 4h minus 3, but everything that's left better have an h in it or you've goofed. I forgot to cancel the 3's there for a second. If I had written this, that can't be, that's impossible because this h in the bottom needs to cancel out. Everything that's left at this point will always have an h in it on top. That way you can cancel it and we just get 4. So the second derivative of that original function is just the constant 4. Now, you may have noticed a pattern here. This is what's going to happen. Anytime you have a polynomial, every time you take the derivative, the degree goes down by 1. So the original function was second degree. His derivative, his first derivative, was first degree. His second derivative was 0 degree. So I went from degree 2, degree 1 to degree 0. A constant function is degree 0. It's a good place to stop.